Today my talk is on nanoscale control of the metal-insulator transition at non-aluminate potassium tantalate 110 and 111 interfaces. Correlated oxide systems has many interesting properties, such as superconductivity and ferromagnetism. The fabrication of nano devices enable us to investigate quantum simulation, quantum transport, and quantum sensing. Creating nanoelectronics at oxide systems will reveal the underlying properties of the system, and vice versa, correlated oxides will add richness to mesoscopic devices. In our lab, we are interested in creating nanoelectronics devices at the interface of lanthanum-aluminate strontium tantalate heterostructure, generally with two techniques: conductive atomic force microscope lithography and ultra-low voltage electron beam lithography. For conductive AFM lithography, we first deposit gold titanium electrodes to make contact with LAO-STO interface. Then we use a biased AFM tip to create devices. When we sketch with positive voltage on the tip, it leaves protons on the surface of LAO which attract electrons to the interface. The interface will become conducting locally, and this process is reversible. When sketching with a negatively biased tip, the interface can be restored to insulating, which allows us to make barriers on the device. The resolution we can typically achieve is around 10 nanometer. Another newly developed technique is ALV-EBL. The concept is when you expose some part of LAO-STO to electron beam, the interface becomes conducting locally. Most of the time, we would like the acceleration voltage to be low, around several hundred volts, to avoid damaging the sample. Compared to conductive AFM lithography, the advantage of this technique is its high writing speed and large working area. It is very suitable for creating large two-dimensional devices. With these two techniques, we realized some exotic devices on LAO-STO platform, including nanowires, terahertz generator and detector, single electron transistor, and electron waveguides. Potassium tantalate is a new platform that attracts much attention recently. It has similar perovskite structure as STO, although the conducting band comes from 5D electrons of tantalum, which has much stronger spin-orbit coupling than STO. LAO KTO 111 and 110 interface has shown superconductivity with Tc almost one order of magnitude higher than STO. To further utilize these properties, one would think of creating KTO-based nano devices. Thus, we tried the two techniques that worked on LAO-STO heterostructures to see if they can create nanoelectronics at KTO systems. First, we tested conductive AFM lithography on an intrinsically insulating 3 nanometer LAO on KTO 110 sample. This is an AFM topography scan on a writing canvas. Surrounding the canvas, there are 16 metal electrodes that contact the interface. We sketch the green region with positive 16 volt on the tip, including the green triangles first and then the green path. In the meantime, we are monitoring the conductance between these electrode pairs. As soon as this green path is finished, a 4-terminal conductance jump around 300 nanosiemens can be observed, indicating a connecting channel is formed at the interface. This process is reversible. When we sketch across along the little red path with negative 8 volts on the tip, the conductance drops back to 0. By fitting the conductance drop with this equation, we get the width of the nanowire, which is around 20 nanometer. The conductance value and the width of the nanowire is comparable to the nanowires created at LAO-STO interface. Thus, we believe the writing and erasing mechanism here is the same, which is the surface charging of LAO surface. We also performed ULV-EBL on the KTO samples. We contact the interface with aluminum wire bonding. The acceleration voltage is set to be 500 volt. During ULV-EBL, we expose the blue area first, and then we expose the green main channel 3 times, each time with 10 microcoulomb per centimeter squared dose. You can see each exposure results. Each exposure results in a conductance jump. The final 4-terminal conductance of this device reaches 6 microsiemens. This device is transferred into a dilution fridge after the exposure. It remains metallic down to low temperature. At base temperature around 50 millikelvin, we can observe a flat region in the 4-terminal IV measurement, corresponding with a superconducting state with a critical current around 18 nanoamp. From the resistance versus temperature measurement, we can extract the critical temperature at half of the normal state resistance, which is at 156 millikelvin. The upper critical field is measured to be 140 oyster. Since the dielectric constant of KTO raises up to 5000 at low temperature, we are able to tune our device by applying a backgate voltage. From the Hall measurement down at 700 millikelvin, we can extract the carrier concentration and mobility. Carrier concentration can be tuned from 6 to 8 times 10 to the 12th per centimeter squared, which is 1 order of magnitude lower than the previously reported in van der Pol measurements at KTO 110 and 111 interface. We think the low carrier concentration can be related to the low TC of this device. In this graph of normalized resistance versus temperature, we can extract that the TC also increases monotonically with carrier concentration, indicating the device is at an underdoped regime. In a separate device patterned elsewhere by ULV-EBL, we also saw relatively low carrier concentration in the 10 to the 12th order, when the sheet resistance of the device is gated to be over H over E squared, which is around 26 kiloohm. As the temperature decreases, it shows a slight upturn. The device appears to go through a quantum phase transition and enters a localization regime. We also demonstrate a one-dimensional nanowire device at LAO KTO 110 interface. Here is the 16 micron long nanowire exposed at ULV-EBL. At a low temperature in the conductance plot as a function of bias voltage and gate voltage, we see diamond-shaped low conductance regions. The line cut at zero bias show a series of conductance peaks. The overall behavior is very similar to a single electron transistor. We believe that the disorder potential has produced a quasi-one-dimensional island. The resonant tunneling through the island gave rise to this transport characteristic. Further experiments are needed in order to effectively create and manipulate single electron transistor devices at KTO interface. Finally, I would want to show that the two techniques that we applied on LAO KTO 1110 samples so far also works on LAO KTO 111 sample. We can write and erase nanowires in AFM, and we can also expose it to E-beam to make it conducting. In summary, with Conductive AFM Lithography and ULV-EBL, we are able to create reconfigurable nanoelectronics at LAO KTO interfaces. The device we created showed tunable superconductivity at low temperature. We also observed single electron transistor-like behavior in a nanowire device. In the future, we are aiming to create nano devices which can give us insight to the underlying mechanism of superconductivity in KTO. Thank you.